Let's be honest, when most people hear the term statistics, they picture complex equations and endless numbers. It can feel overwhelming, right? But here's the good news. Understanding and applying statistics in critical appraisal doesn't have to be intimidating. In this tutorial, we'll simplify it for you. We'll explore two key branches of statistics, descriptive and inferential, and discuss how they are used to evaluate and interpret medical research. These tools are essential for critical appraisal, helping you to assess the quality, reliability, and applicability of data in studies. By the end of this session, you'll have the confidence to navigate research findings like a pro. So, let's start by breaking down what descriptive and inferential statistics are and why they matter in critical appraisal. First, descriptive statistics. Descriptive statistics provide the foundation for understanding research data. Think of them as the first step in making sense of a dataset. They summarize, organize, and present data in a way that's easy to interpret. Descriptive statistics answer the question, what happened? So what are the key functions of descriptive statistics? 1. Summarizing data. By reducing complex datasets into manageable summaries, such as averages or percentages, descriptive statistics allow you to quickly grasp the overall picture. 2. Organizing data. Tables, charts, and graphs make it easier to identify patterns and trends. 3. Presenting data. They offer a clear and concise way to share information, especially with non-technical audiences. Now that we've introduced descriptive statistics, let's break down the key types and what they tell us about a dataset. Descriptive statistics can be grouped into three main areas: measures of central tendency, measures of dispersion, and frequency distribution. Each plays a unique role in helping us understand data. Let's start with measures of central tendency. These are tools that help us understand the center or typical value in a dataset. They include the mean, median, and mode, each providing a slightly different perspective. First, we have the mean, or what most of us call the average. To calculate the mean, you add up all the values in the dataset and then divide by the total number of values. For example, if our dataset is 3, 7, 7, 8, and 10, we calculate the mean like this: 3 plus 7 plus 7 plus 8 plus 10, divided by 5 equals 7. So the mean in this case is 7. Next is the median, which is the middle value when the data is arranged in ascending order. Using the same dataset, 3, 7, 7, 8, and 10, we see that the middle value is 7. So the median is 7. If there's an even number of values, the median would be the average of the two middle numbers. Finally, we have the mode, which is the most frequently occurring value in the dataset. For our example, 3, 7, 7, 8, and 10, the number 7 appears most often, so the mode is 7. To recap, the mean gives you the average. The median identifies the middle value. The mode highlights the most common value. Each of these measures is useful for summarizing data, but the best choice depends on the context of your analysis. For example, if your data has extreme values, the mean might be misleading, and the median could provide a better sense of the center. Now, let's talk about the range, which is one of the simplest measures of dispersion. The range tells us how spread out the data is by calculating the difference between the highest and lowest values in a dataset. For example, if we have the dataset 3, 7, 7, 8, and 10, we calculate the range by taking the maximum value, which is 10, and subtracting the minimum value, which is 3. So, the range is 10 minus 3 equals 7. This means the data is spread across a range of 7 units. While the range gives us a quick idea of variability, it has a limitation. It only considers the two extreme values and ignores the distribution of the data in between. That's where other measures, like variance and standard deviation, come into play for a more detailed picture. Variance. This tells us how far each value in the dataset is from the mean on average. It's calculated by taking the squared differences from the mean and averaging them. Standard deviation, a more intuitive measure derived from the variance. It shows on average how much the values deviate from the mean. A smaller standard deviation means the data points are closer together, while a larger one indicates they're more spread out. Understanding dispersion is critical when interpreting study results because it helps us gauge how consistent or variable the data is. 3. Frequency distribution. Finally, frequency distribution tells us how often each value occurs in the data set. This is typically presented visually through tables. Summarize the frequencies of values. Histograms and bar charts show the distribution of data visually, making patterns easy to spot. For example, imagine a data set of exam scores. 10, 20, 20, 30, 40, 40, 40. A histogram would clearly show that 40 is the most common score. So how does this apply to critical appraisal? Descriptive statistics are the foundation of any research analysis. They help you understand the study population. For example, summarizing participant demographics like age, gender, or health conditions. Identify patterns in outcomes, such as the distribution of treatment responses or baseline measurements. Prepare for deeper analysis. By summarizing the data, you're better equipped to move into inferential statistics, which we'll discuss next. By mastering descriptive statistics, you gain the tools to dissect a dataset's basic characteristics, setting the stage for a more comprehensive evaluation. Now that we've covered descriptive statistics and how they help us summarize data, let's move to the next step. Inferential statistics. Imagine you've collected data from a sample group, say 200 patients in a clinical trial. Descriptive statistics can tell you the average blood pressure in this group or how many patients responded to a treatment. But what if you want to take this information and make conclusions about a much larger group, like the entire population of patients with the same condition? That's where inferential statistics come in. Inferential statistics allow us to move beyond the data we have and make educated guesses or inferences about a larger population. It's like looking at a small puzzle piece and using it to predict what the whole picture might look like. This is critical in research because we rarely have the time, resources, or ability to study an entire population. Instead, we use a sample and let inferential statistics do the heavy lifting. So, what are the key concepts of inferential statistics? To truly understand inferential statistics, we need to explore a few core concepts. Don't worry, I'll keep it simple and practical. Population versus sample. Let's start here. A population is the entire group you're interested in, like all patients with diabetes in the world. A sample is a smaller group selected from the population, like 500 patients from a specific region. The idea is that by analyzing the sample, we can learn about the population, assuming the sample is representative. Think of it as taking a small sip of soup to decide whether the entire pot needs more salt. Hypothesis testing. This is where we test assumptions or claims about the population. Every hypothesis test begins with a null hypothesis, H0, essentially saying there's no effect, no difference. The alternative hypothesis, H1, on the other hand, says, yes, there is a difference. For example, if you're evaluating a new drug, the null hypothesis might say, this drug has no better effect than the standard treatment. Using inferential statistics, you can analyze the data to see whether you have enough evidence to reject the null hypothesis. Confidence intervals. A confidence interval tells you how certain you can be about a population parameter, like the average blood pressure. For example, if you calculate a 95% confidence interval of 120, 130, you're saying there's a 95% chance the true population average falls within that range. It's not perfect, but it gives you a level of assurance. Now, let's talk about some of the techniques researchers use. These are tools that help us make inferences about the population. Estimation. This involves using sample data to estimate population parameters. Think of it like guessing the average height of all adults based on a smaller group. Estimation comes in two flavors. Point estimate, a single value, like saying the average is 170 cm. Confidence interval, a range, like saying the average is between 168 and 172 cm, with 95% confidence. Regression analysis. Regression helps us understand relationships between variables. For example, it can predict patient recovery time based on factors like age or treatment type. It's like saying, if we change X, how will Y respond? Hypothesis testing. This goes hand in hand with p-values. If your p-value is below a certain threshold, usually 0.05, it means the results are statistically significant. In plain language, it means the effect you're seeing is probably real and not just due to random chance. Chi-square tests and ANOVA. These are used to compare groups. Chi-square is great for categorical data, like determining if smokers are more likely to develop a specific condition. ANOVA, on the other hand, is for comparing averages across multiple groups, like evaluating 3 different drug doses to see which works best. So how does all this fit into critical appraisal? Inferential statistics help us answer big questions. Are the study's findings real, or could they be due to chance? How confident can we be in the results? Can the study's conclusions be applied to other populations? For example, if a study claims a new treatment reduces symptoms by 30%, inferential statistics allow you to evaluate whether that effect is statistically significant and whether it's likely to hold true for other patients beyond the study sample. But here's the catch. Inferential statistics are based on assumptions. If the sample isn't representative or the data doesn't meet certain criteria, the conclusions might be flawed. This is why understanding these techniques and their limitations is so important in critical appraisal. Now that we've explored both descriptive and inferential statistics, let's take a moment to compare the two and see how they complement each other. These two approaches are like different tools in your statistical toolbox, each with a distinct purpose. First, let's talk about purpose. Descriptive statistics are all about summarizing and describing the data you already have. They provide a snapshot of what's happening within your data set, things like averages, ranges, and frequencies. Inferential statistics, on the other hand, take it a step further. They're about making inferences, using the data you have to draw conclusions about a larger population. It's like moving from understanding what happened in your sample to predicting what could happen in the real world. Next, there's the data source. Descriptive statistics work with the entire data set. If you have data from a clinical trial with 200 participants, you're analyzing all 200 participants directly. Inferential statistics, however, often start with a sample, a smaller subset of the population. The goal here is to use this smaller group to make generalizations about a much larger population, like all patients with a certain condition. Finally, let's compare the techniques. Descriptive statistics focus on measures of central tendency, like the mean, median, and mode, and measures of dispersion, like standard deviation or range. They answer questions like, what's the average response? Or, how spread out are the results? Inferential statistics use different techniques, such as estimation, hypothesis testing, and regression analysis. These methods help us answer deeper questions, like, is this treatment really effective? Or, what's the likelihood that these results are due to chance? Together, descriptive and inferential statistics provide a full picture. Descriptive statistics set the stage by organizing and summarizing your data, while inferential statistics help you interpret those findings and apply them to broader contexts. Both are essential for a thorough and meaningful critical appraisal of research. Now, let's bring it all together. How do these statistical tools fit into the process of critical appraisal? Descriptive statistics in critical appraisal. Use descriptive statistics to understand the study population's demographics, such as age, gender, or medical history. Examine outcome distributions to identify trends or anomalies in the data. Visualize data to make findings more accessible and easier to interpret. Inferential statistics in critical appraisal. Use inferential techniques to assess the reliability of study results, such as the significance of treatment effects. Evaluate hypotheses to determine whether the observed outcomes are likely due to chance. Generalize findings to broader populations while considering confidence intervals and potential sampling errors. By combining both types of statistics, you ensure that your appraisal is thorough, objective, and rooted in evidence. So, ladies and gentlemen, mastering statistics for critical appraisal. Statistics might seem daunting, but they are essential tools for anyone engaging in critical appraisal. Descriptive statistics provide the foundation, helping you summarize and understand the data, while inferential statistics allow you to draw meaningful conclusions and make evidence-based decisions. Remember, the goal is not just to analyze data, but to use it to evaluate the quality and applicability of research. By mastering these statistical concepts, you'll enhance your ability to critically assess medical studies, identify reliable findings, and contribute to better decision-making in your field. Thank you for joining this tutorial. Keep practicing, stay curious, and let statistics empower your critical appraisal journey. Please refer to the training module of this tutorial and let me know if you have any questions or need more resources. Thank you again, and see you soon.